Hello, I'm Chung-Hsien from National Tsinghua University. Today I'm presenting linear time mixed cell height legalization for minimizing maximum displacement. Let's go through today's outline. First of all, in introduction, I will introduce the adoption of mixed cell height circuit, resulted challenges, and give the problem formulation. In the second section, I will focus on our main contribution, which is the proposed approach to deal with mixed cell height legalization problem. Then I will use experimental results to analyze the solution quality of our algorithm and compare with state-of-the-art works. Finally, the wrap-up will be put in the conclusion section. Let's start from introduction. With the fast-growing complexity and the shrinking number of routing tracks within standard cells, mixed cell height circuits are adopted for more advanced technology nodes. In this framework, cells with complex function or large driving power can be designed as double or even multiple road height, while simple cells can be still designed as single road height. Indeed, the adoption of multiple road height cells successfully solves the problem caused by technology scaling and provides more flexibility on circuit design. But every coin has two sides. They lead to some challenges in the VLSI design flow. To be specific, we are solving the emerging challenges on the legalization stage. I will briefly introduce the legalization stage. Legalization occurs after global placement and before detail placement, targeted at removing overlaps among cells and aligning them to the placement sites on rows. As its name suggests, an ideal legalizer should only deal with legalizing cells. It should preserve the quality of global placement as much as possible. So the usual objective for a legalizer will be average cell displacement and maximum cell displacement compared to global placement. The figure below is an example of before and after the legalization stage. We can see that all of the cell overlappings are solved, and every cell is aligned to row after legalization. Here are some challenges regarding multiple road height cells. In order to reduce the problem complexity of legalization, traditional legalizers process the circuit row by row. With multiple road height cells, we can no longer consider each row of a design independently. Obviously, this escalates the difficulty of legalization. In addition, since there are cells crossing rows now, we should also take care of the power rail alignment constraint, as pointed out in earlier papers. For odd row height cells, the problem can be trivially solved by flipping them horizontally, while even row height cells should be placed in every other row with proper power rails. So here is the problem formulation. The input will be a global placement where there are cells of multiple row height. The output will be a legalized placement with maximum cell displacement and total cell displacement minimized, such that cells must be placed inside the layout region. Cells must not overlap with one another or with the pre-placed macros. Cells must be located at placement sites on the rows. Cells must be placed in rows with proper power ground rail alignment. So let's move on to the proposed approach. This is the overall flow of our approach. There are three stages in the flow. In the first stage, which is preprocessing stage, we decide to obtain a good initial row assignment and soldering, rather than using the one from global placement. The second stage includes two algorithms. Both are targeted at minimizing maximum displacement. Empirically, Many cells are still movable without harming the optimal maximum displacement after the second stage. So, we decide to add an additional refinement stage to minimize total displacement. After that, we will get the legalization result. As previously mentioned, we want to find a good initial cell ordering and row assignment in preprocessing step. Since completely following the cell ordering of global placement tended to create a lot of dead space, which will affect both placement feasibility and optimality. The figure shows an example. In this case, the yellow and green cell cannot be placed in the highlighted area under current cell ordering, even when there are abundant space here. Thus, we decided to obtain a good initial row assignment and ordering of cells using multi-row global legalization from reference paper 4, MGL for short. It ensures that placement legalization under this initial row assignment and cell ordering is feasible. Since MGL targeted at minimizing total displacement, there must exist a high-quality legalized placement in terms of total cell displacement under this initial row assignment and cell ordering. In iterative cell swapping, we try to minimize the maximum displacement by swapping cells. In each iteration, we will first locate the maximum displacement cell, Cmax. Its displacement is denoted as displacement max. In the example, the global position of Cmax is denoted as symbol X, and the value of displacement max is 3 in this case. Then, we will pick a target cell C-target within displacement max from the GP position of Cmax. This is the C-target we found. If swapping Cmax and C-target reduces the maximum displacement and will not increase the total displacement, we swap those cells. We can see that in this case, after the swap, total displacement and maximum displacement has decreased, so we will keep the result. In addition, we will prefer a target cell C-target with dimension as close to Cmax as possible. After each swap, we check if the new placement is still legalizable. If not, we will simply revoke the last cell swap and proceed to next step. In deck-based legalization, we try to minimize the maximum displacement under fixed row assignment and cell ordering. We will build a deck and use it to facilitate the dynamic programming-based computation of each cell's shifting amount. It is guaranteed to have optimal maximum displacement after applying the calculated shifting amount to each cell. I will quickly go through the basic idea of this algorithm. First of all, we will build a deck G such that every edge ij in G exists if and only if cell j, denoted as Cj, is immediately on the right of Ci in some row. For every edge ij, we define its length as deficit Sij. Deficit Sij indicates the minimum related right movement of Cj with respect to Ci in order to avoid any overlap of cells on the path from Ci to Cj. Obviously, if edge ij belongs to G, then Sij equals to Wi minus xj head minus xi head, where x head is the global position. Else, we will find P start ij, which is the path from Ci to Cj in G with the largest total cell width, and W star ij is the total width of all cells in P star ij. Then the equation can be written as follows. After we build the deck and calculated deficit defined in the previous page, we need more terms to determine the shift amount for each cell. The formulations of 4 additional terms, low I, theta I, Li, Ri, are listed on the slide. They only require deficit and the magnitude of delta Y to calculate. After we have the 4 terms for all of the cells, we can obtain each cell's shift amount using this formula. Applying the shift to each cell, and we can have a legalized placement with optimal maximum displacement. For detailed proof, please refer to the paper. After running the deck-based legalization, we get the cell positions for optimal maximum displacement under the given row assignment and cell ordering. But actually, many cells are still movable without harming the optimal maximum displacement. So we added this stage, trying to minimize total displacement under fixed row assignment and cell ordering. The basic idea of this stage is as follows. We make cell clusters and relocate the cells inside the same cluster together to minimize the total displacement, while keeping the relative distance between cells inside the same cluster. Then, we will uncluster all cells and horizontally shift each cell to reduce its displacement. Then let's move on to the experimental results. This is the detailed information for each benchmarks. All of them are from ICCAT 2017 contest. Each of them contains different percentage of multiple row type cells, microcount, and utilization for realistic experiment. We compared our result with 2 state-of-the-art works, Reference Paper 4 and Reference Paper 5. Compared with Reference Paper 4, our algorithm achieves 1% smaller delta HPWL, 11.1% smaller maximum displacement, while having 1.1% larger average displacement. Compared with Reference Paper 5, our algorithm achieves 11% smaller delta HPWL, 11.2% smaller maximum displacement, and 4.1% average displacement. We note that Reference Paper 5 obtains smaller maximum displacement than ours in a few designs, due to the difference in row assignment and cell ordering. If we use the same row assignment and cell ordering as Reference Paper 5, then the maximum displacement obtained by our deck-based legalization is guaranteed to be as good as Reference Paper 5. Also, our proposed approach is highly efficient. We compare our runtimes with those by Reference Paper 4 on our machine. Both of Reference Paper 4 and our approach use MGL as preprocessing stage. Column 2 shows the runtime of MGL for each benchmark. Column 3 and column 4 shows the runtime of the subsequent stages of Reference Paper 4 and our approach. We can see that our subsequent stages are about 60.7% faster on average. So let's go to the conclusion. We proposed a mixed cell height legalization approach, which optimizes both the total and maximum cell displacement. It is a highly efficient algorithm with linear runtime, and it guarantees to have high-quality solutions. According to the experiments, 11% smaller maximum displacement compared to the state-of-the-art works with similar average displacement. Thank you.